This is Chapter 8, Summary Notes on Gas Laws. This video will be on the kinetic molecular theory and gas law variables. All right, one of the nice things about working gas law problems is that if you know one gas law, you know them all. And that gas law is identified over here as the ideal gas law. It contains the variables and a constant. All right, so keep that in mind as we go through this particular video. The kinetic theory of gases assumes that the particles that make up the gas are randomly moving and they have very high velocities. Okay, there are attractive forces there, but they're very, very tiny, and since the particles are so far apart, they're deemed negligible. All right, there's mostly empty space. All right, so that's why the particle size is negligible compared to the volume that it is occupying. All right, the particles are moving in straight lines and exerts pressure on the walls of the container. So that's a very important point. Probably the most important part of this is this last one. The Kelvin temperature is directly proportional to the average kinetic energy of the particles. So if you double the temperature, you're doubling the average kinetic energy. And if you're having the temperature, Kelvin temperature, not Celsius, then you are having the average kinetic energy as well. All right, so the next section involves the units that we'll be using to describe a gas. And again, if we take a look at the ideal gas law, these will be the units that we're covering: pressure, volume, moles, and temperature in Kelvin. N is moles. Okay. Pressure is P. All right, and the pressure units, you can see a whole string of them here, and you can even add a few more, but these are all equal to each other. That's the important part about the pressure, because you can do lots of conversions between one unit and another. All right, we're used to hearing the inches of mercury one. When the weather people talk in terms of the barometric pressure, if we have high pressure, it's nice outside. If we have low pressure, it's usually overcast and possibly raining. And hurricanes form. We have an extremely low barometric pressure when a hurricane forms. All right, so there are some conversions to work. We have 475 millimeters of mercury, and we need to change that to atmospheres. So we'll take the part of the string of equalities that will make this happen. All right, so 475 millimeters of mercury. We make a conversion factor so that atmospheres is in the numerator, and what we want to cancel is in the denominator. All right, and work our problem. All right, and bring the calculator up to help us out a little bit here. We have 475. If I can go ahead and get this in right. 475 divided by 760. You know it's going to be less than 1. All right, and it's 0.625. All right, so that equals 0.625 atmospheres, and we've done a conversion. All right, so this next one is just going back the other direction. All right, so if I'm starting with 2 atmospheres, then I want the 760 part on top, and the 1 atmosphere on the bottom, so that atmospheres will cancel. All right, so it's just 2 times 760. All right, and that gives us 1520, I believe. And that's millimeters of mercury. Sometimes I'll call them mercury M&Ms. All right, there's some conceptual questions here next. The downward pressure on mercury in a barometer is equal to, less than, or greater than the pressure of the atmosphere. All right, that is the same as, all right, because that's how the barometer works. All right, if we take a look at the picture that's here, we have an open container that has the mercury in it. All right, and I'll just kind of swath that with the highlighter. Our liquid mercury is in the open pan, so the column of air is pushing down on that mercury. And interestingly enough, this tube that's here, all right, was filled with mercury before it was inverted into that pan. So when it got inverted, some of it dropped down. This could have been an entire meter's worth of tube in order to think about it in terms of millimeters. All right, and some of it dropped down and created a vacuum up here. But the column that of mercury is supported by an equivalent of 1 atmosphere, pushing down on the surface here and supporting this column that we see in the tube. All right, so that's how atmosphere gets measured at sea level. All right, so that's the definition of 1 atmosphere. It's the pressure at sea level. Okay. All right, so this next question says a water barometer is 13.6 times taller than a mercury barometer. Why? All right, because mercury is less dense than water is less dense than mercury. Water's density is only 1, okay? The density of H2O is equal to 1 gram per ml, okay? All right, so the other units that are used in gas law problems is milliliters or liters, and just as long as your unit's the same when you're working with two sets of conditions of the variables, you'll be fine. All right. Temperature, we need to convert our Celsius to Kelvin. All right, and remember the conversion there is Kelvin plus 273. So anytime you see a Celsius temperature, automatically add that 273 to it. Because on the Celsius scale we have a 0 degrees Celsius, but there are no negative signs nor a 0 on the Kelvin scale that would apply to the gas laws. All right, so this is a very important point here. We can't multiply by a 0 and expect to get an answer. All right, it would just be 0. All right, amount of substance in moles. Well, we know that Avogadro's number is 6.02 times 10 to the 23rd particles, but we also know that represents mass in grams, okay? Mass in grams from the periodic table, okay? And it also represents a volume, all right? It also represents a volume of 22.4 liters at STP, all right? If you don't know what STP is just yet, okay, you will find out later in this video. All right, so the next video will work some math problems. All right, but those are the units: moles, temperature, volume, pressure are all involved in the gas laws. And again, PV equals nRT. That's our ideal gas law, and you see all 4 of those plus an R value that is a true constant, and you'll see about that in the upcoming videos.